Welcome back, students. In this lecture we are going to continue what we started in the last lecture with the grid generation. So we finished at this slide, therefore we are going to proceed from this point onwards and see what further analysis can be done. So we talked about grids, right? So there are actually two types of grids. One is a structured grid, and so structured grid means the grids are regular and coherent structure to the mesh layout. Okay, these are the simplest structured grid, and they are generally uniform rectangular grids. Those are called the structured grids. So the structured grids look like this one here. All right. So you see they have a uniform rectangular grid. So all these small shapes are rectangular. All right. So structured grids are not limited to rectangular grids only. So these ones, this could be actually of any shape. Here it shows the rectangular grids only, but you see these rectangular grids are decreasing in size. The second one are the unstructured grids. So the grid cell arrangement is irregular and has no symmetric pattern. If you see in the last one, there was a symmetry pattern here. If you consider this one, you see symmetry across this, and here it is completely symmetric, this one. In the unstructured grids, the cell arrangement is irregular and has no symmetric pattern, something like this. Okay. So see the triangles, these are of no specific same type. You see these cells here are very small, smallest is smaller than these ones here. Largest. Okay. So now after this grid generation, we comes to the solver stage. So in this stage, that the governing differential equations are solved by an approximate numerical technique after specifying the boundary and the initial conditions. All right. So the actual real solution of those differential equations is done at this stage, called the solver stage. And in post processing, the extraction of results and visualization how the results appear is done. So when it comes to extraction of results and visualization, flow field variables are plotted and analyzed graphically. So this is the most common thing to do in the post processing. So you know we mentioned about boundary and initial conditions, and that is what we are going to discuss next. So boundary condition, the same governing equations are valid for all compressible Newtonian fluid flow problems, right? So if the same equations are solved for all types of problems, then how can we achieve different solutions for different flow situations involving different geometries? That is the question. Because which governing equations are we going to talk? We are talking about the continuity equation, Navier-Stokes equation. So this is common for all the fluid flow problems, right? Then how do we know and how do we achieve different solutions for different flow situations involving different geometries? And this happens because of something called boundary conditions. So the answer is boundary conditions of the problem. So boundary conditions, I will tell you what that is. For example, if the flow is occurring right in a tank itself, the velocity is like 1 meters per second. This is one continuously occurring, right. So, this is one boundary condition. There could be other where the velocities could be 10 meters per second, for example. So, these are different boundary conditions, that is why we get different results. Suppose one of the boundary conditions could be this is closed at this end and the other one that it could be open. So, this is another boundary condition. So, because of this difference in boundary conditions, we have different solutions of the problem. Now, as I said, I mentioned about being closed and being open. There is a wall at the boundary. These wall and other concepts you have read in your previous lectures of hydraulic engineering. So, we are going to talk about the wall boundary condition. Since fluid cannot pass through a wall, the normal component of the velocity relative to the wall is set to 0. And this is, what is this called? This is called no slip condition. And therefore, due to the no slip condition, the tangential component of the velocity at a stationary wall is set to 0. All right. So, you see there, if there is an inlet here, there is a wall here, there is a wall here, there is an outlet. So, the velocity at this point does not matter what the velocity here is, at this particular point anywhere around across this wall, the velocity will be 0 due to no slip condition. All right. Now talking about the inflow and the outflow boundary conditions. So, you see this is inlet, this is outlet. So, from here the inflow will be there and from here outflow will be there. In means coming in and out means going out. So, at a velocity inlet or outlet, the velocity of the incoming or outgoing flow is specified along the inlet outlet phase. At pressure inlet and outlet, the total pressure along the inlet and outlet phase specified. So, the inlet and outlet can be, the specification can be in two forms, whether we want to specify the inlet, whether the flow velocities at the inlet or outlet or the pressure. One typical example here is for the pressure is the pipe flow. Here it is open channel flow. All right. So, there is one question which I would want to solve or discuss. So, there is a CFD code which is used to solve a two dimension x and y incompressible laminar flow without free surface. Okay. The fluid is Newtonian. Okay. So, appropriate boundary conditions are used. So, the question here is now list the unknowns in the problem and then list the corresponding equations to be solved by the computer. So, first important information that we have is that it is two dimensional in nature, correct. So, the unknowns, you can start guessing the unknowns. First is going to be velocity u, which is along x direction, correct. Secondly, the velocity v, which is along y direction. The third one is going to be, since there is no third dimension, there is not going to be a w velocity, but there definitely will be p, that is pressure. And how are we going to solve these, which equations are we going to solve for u, v and p? We are going to use see there are 3 unknowns, so we must have 3 equations. So the first equation is very common conservation equation, which is the continuity equation. The second one will be the x momentum equation. So momentum equation in x direction. And we will have a y momentum equation. All right. So this was very quite simple to imagine or guess that in 2 dimension only 2 dimensional velocities and the pressure is going to be the unknown, and therefore to solve we just need the 3 equations as continuity, x momentum and y momentum equations. All right. So now we come to in the solver stage we come to we have mentioned about the boundary condition, and now we come to discuss about the partial differential equations. So a partial differential equation PDE is an equation stating a relationship between a function of 2 or more independent variables and the partial derivatives of this function with respect to the independent variable. So this is the definition of partial differential equation. Okay. So it states a relationship between a function of 2 or more independent variables and the partial derivatives of this function with respect to the independent variable. Okay. For example, this equation del square f by del x square plus del square f by del y square is equal to 0. Okay. So these are independent variables x and y, and f is a dependent variable, and this equation is called Laplace equation. From your previous experience you should be knowing this. Another equation is del f by del t is equal to alpha del square f by del x square. Okay. So this is a diffusion equation. The third equation which we have written is del square f by del t square is equal to c square del square f by del x square, and this equation is a wave equation. So these are the 3 most common types of equation, right, in partial differential equation that we know. So the solution of the partial differential equation is that particular function f x y or f x comma t which satisfies the partial differential equation in the domain of interest. Domain is given by dxy or dx comma t. Fxy is when the function is based only on x and y, fxt when if it is dependent on only x and t. All right. Further, f of x comma y or f of x comma t, these are 2 different type of partial differential equations, fx comma y or fx comma t. They also satisfy the boundary and or initial conditions specified at the domain of interest. So they must be satisfied at all places in the domain or at all times for which the calculation is being done. So taking a slight detour because it's important that we try to remember what the classification of partial differential equations look like. So a general quasi-linear second order non-homogeneous partial differential equation in two independent variables can be written as a fxx plus b fxy plus c fyy plus d fx plus e fy plus f into f. This is a general quasi-linear second order. We have x, y and y, that is second order non-homogeneous partial differential equation. So, a, b and c may depend on x, y, fx and fy. Okay. D, E and F may depend on x, y and f. So, this means quasi-linear. All right. G is non-homogeneous term and may depend on x and y, that is why we read non-homogeneous. Okay, this is not equal to 0. So, the classification depends on the sign of the discriminant b square minus 4c as. So, in this particular equation a fxx plus b fxy plus c fyy plus d fx plus e fy plus ff is equal to g, the solution will depend on the value of b square minus 4ac. And how does it depend? If b square minus 4ac is less than 0, then it is going to be elliptical partial differential equation. If b square is equal to 4ac, it is going to be a parabolic partial differential equation. If b square minus 4ac is greater than 0, then it is going to be a hyperbolic partial differential equation. This you can recall from your mathematics class. Now, going to domain of dependence and range of influence. So, if we consider a point P in the solution domain, so there is a point in the domain P and let the solution at P, if we assume that the solution at that particular point P is fxp comma yp, we assume that, then the domain of dependence of P is the region of solution domain upon which fxp yp depends. All right. So, region of influence of P is the region of solution domain in which the solution of x comma y, f of x comma y is influenced by the solution at P, which is fxp comma yp. So, for an elliptical partial differential equation, the entire solution domain is both the domain of dependence and range of influence of every point in the solution domain. So, there are two things: domain of dependence of P, and secondly there is a range of influence of P, which we have defined as the domain of dependence of P is the region of solution domain upon which xp f of xp comma yp depends, whereas the range of influence of P is the range of solution domain in which the solution of f of x comma y is influenced by the solution at P. All right. So, applying this to an elliptical partial differential equation, the entire solution domain is both the domain of dependence and the range of influence of every point in the solution domain. All right. So, the horizontal hatching here, these ones, shows the domain of dependence, whereas the vertical hatching shows the range of influence. Now, for a parabolic PDE, this is the domain of dependence. So, horizontal hatching, whereas the vertical hatching, like these ones, these are the range of influences. Okay. For a hyperbolic partial differential equation, the horizontal hatching shows the domain of dependence, this one, whereas the vertical hatching shows the range of influence. So, for three different type of solutions we said profiles, elliptical PDE, parabolic PDE and hyperbolic PDE. For elliptical PDE we have seen that the domain of dependence is the entire solution and also the domain of dependence, whereas for parabolic and hyperbolic PDE, the horizontal hatching as shown in the figures here shows the domain of dependence, whereas the vertical hatching shows the range of influence. Now, the classification of the physical problems. The physical problems can be classified into equilibrium problems or propagation problems. The third is eigen problems. Okay. So, any physical problems can be classified into three different forms. What are the equilibrium problems? Equilibrium problems are the steady state problems in closed domains. Steady state means there is no dependence on time, there is an equilibrium. So, example is Laplace equation of such type of problems. So, here the solution f of x comma y is governed by an elliptical partial differential equation subject to boundary conditions specified at each point on the boundary B of the domain. So, solution of Laplace equation is governed by an elliptical partial differential equation. This is an important thing to remember. Okay, and of course, the solution will depend upon the different type of boundary conditions that has been specified at each point on the boundary B of the domain. So, we have to specify, suppose this is the so we have to specify boundary here also, here also, here also, at all those points. Something like this. So, if this is the figure, you see because this is an elliptical PDE, the domain of dependence and range of influence are same, all the domain, and this is the boundary. So, we should be able to supply the boundary conditions at all the points, okay, which is denoted by B here. The second type of problems are propagation problems. So, an example is initial value problems in open domains. So, open with respect to one of the independent variables, example time. The solution f of x comma t in the domain is marched forward from the initial stage. Okay, so, we know things at time t is equal to 0, then we go from time t is equal to 0 to let us say time t is equal to 1, then time t is equal to 2, and then time t is equal to 3 seconds. So, the marching of the solution is guided and modified by the boundary conditions. So, if we have a different boundary condition, we still have to specify the boundary condition at time t is equal to 0, initial point, and we will also have to specify the initial problems at initial values at all the points in the domain. So, boundary conditions and also the value at all the points in the domain initially too. Example 1 here is the diffusion equation. You see this is an open boundary and we have to go from it is in x and this is in time t. This is x direction. So, this are solved by the parabolic partial differential equation, parabolic PDE diffusion equation. Second example is a wave equation. So, the wave equation is solved by the hyperbolic PDE, hyperbolic partial differential equation. So, as we have seen, three different type of equations have different partial differential equation profiles. One was elliptical Laplace equation, the diffusion equation has parabolic partial differential equation, and a wave is hyperbolic partial differential equation. Now, the last one in this set is the eigen problems. So, problems where the solution exists only for special values of parameter of the problem. Okay, so the solution will not be there for all the values of the parameters. So, and these special values are called the eigenvalues. Hence, these problems have involved additional step of determining the eigenvalues in the solution procedure. So, this is about the 4 type of problems that we were talking. Okay. So, now from this point onward we will proceed to the discretization technique, that is we start with the finite difference method first. So, there are significant benefits in obtaining a theoretical prediction of a physical phenomenon. All right. So, the phenomenon of interest here are governed by differential equations. Concept, that is replacing the continuous information contained in the exact solution of the differential equation with discrete values. All right. There is something called the Taylor series formulation which we generally use. Usually, finite difference equation consists of approximating the derivatives in the differential equations via truncated Taylor series. So, how do we approximate the derivatives in the differential equation? Using a truncated Taylor series, which looks like this. I am pretty sure you have read that in your maths class. So, phi 1 is written as phi 2 minus delta x del phi del x at 2 plus half delta x whole square del phi del x whole square at 2, you know. So, and series like this goes on with alternate minus and plus signs. So, this is called the truncated Taylor series, or phi 3 can be written as phi 2 plus delta x del phi del x plus half del x square, and it can go on like this. All right. So, truncating the series just after the third term, adding and subtracting the two equations. So, if you see, there were two equations, phi 1 and phi 3, both were written in terms of phi 2. If what we do, if we just if we first stop the series after the third term and we add and subtract the two equations, then we obtain del phi by del x at point 2 will be phi 3 minus phi 1 by 2 delta x, and also del square phi by del x square can be written as phi 1 plus phi 3 minus 2 phi 2 by delta x square. Okay. So, what we have seen here, we have used the truncated Taylor series in general to write these values phi 1 and phi 3 and phi 2, and once we add those and once we subtract those, we get terms like these. So, the substitution of such expression into differential equation leads to finite difference equation. Okay. Say like this. So, analytical solution of the partial differential equation provide us with closed form expressions which depict the variation of the independent variable in the domain. All right. So, this is the domain here. And the numerical solution based on finite differences provide us with the values at discrete points in domain which are known at grid points. So, there is a difference between the analytical or the mathematical solution. What does analytical solution of the partial differential equation provide us? They provide us with closed form expressions which depict the variation of the dependent variable in the entire domain, whereas using the numerical simulation based on finite difference, it provides us with the values at discrete points in the domain. So, it will provide us the value here, 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 whereas mathematical solution will give us closed form expression which is valid everywhere. alright, not only at some points. So, of course, if we are able to obtain the analytical solution, that is the best case scenario, but in most of the cases, actually majority of the cases, we are not able to do that. Therefore, we resort to the technique of finite difference method. Okay. So, I think this is a nice point to stop, and in the next lecture we will start with elementary finite difference quotients. So, thank you so much for listening, and I will see you in the next lecture.